That is exactly what scientists are now trying to understand as we enter April 15, 2026. Just 14 hours ago, NASA's Solar Dynamics Observatory recorded something from 3I Atlas that almost no known natural process can explain. The data suggests a focused and stable magnetic connection forming between the object and the outer atmosphere of the Sunday. The probability of this happening naturally is estimated at just 0.002%. Now pause and imagine what that actually means. An object roughly 140 million kilometers away is not only interacting with the Sun, but appearing to form a structured link, like a magnetic bridge made of energized plasma, and through that bridge, something even more unusual is happening. Material is being pulled directly from the Sun's outer layer, specifically helium 3. This is not a passive interaction. It looks like a controlled transfer. The European Space Agency's solar orbiter confirmed the same event at 4:18 UTC. Their instruments recorded a localized reduction in solar mass activity, paired with a tightly focused stream of helium-3 moving against the solar wind traveling outward toward 3I Atlas instead of away from the Sunday. That detail is critical. Under normal conditions, solar material expands outward in chaotic streams driven by solar wind. But here, the movement is organized, directed, as if something is pulling it in a specific direction. NASA's Parker Solar Probe added another layer of confirmation. It detected that the energy within this plasma connection is not dispersing randomly into space. Instead, it is confined within a narrow magnetic channel about 400 kilometers wide, maintaining structure across millions of miles. That level of stability is extremely unusual. To sustain a magnetic structure like that, calculations suggest an energy output on the order of 4.2 petawatts would be required continuously. That is not a small fluctuation. That is a massive, sustained power system operating in one of the most unstable environments in the solar system. And here is where the situation becomes even more difficult to explain. Because if this were a normal comet, the Sun's environment should destroy it instantly. The heat, radiation, and magnetic turbulence would tear it apart completely. No known natural object could remain intact while interacting at this intensity. Yet 3I Atlas remains structurally stable. It is not fragmenting. It is not breaking apart. It is maintaining a consistent form while staying locked into this magnetic connection. Even researchers at Caltech and NASA's Jet Propulsion Laboratory are now openly acknowledging how unusual this dataset is. The working assumption that this is a simple interstellar comet is no longer sufficient to explain the observations, because the data is clear. Something is actively drawing material from the Sunday. And this is only the beginning of the pattern. To understand why this is so important, we need to go back to how 3I Atlas was first identified and why its early behavior already hinted that something was not normal from the very start. Because to understand what is happening now, we have to go back to the moment 3I Atlas first entered our detection range and the first signs that it was not behaving like a normal interstellar object. When it was officially catalogued on August 24, 2025, it was initially labeled as a standard interstellar comet. At first glance, it appeared similar to previous visitors like Oumuamua and 2I Borisov. Nothing in the early classification suggested anything unusual. But that assumption began to weaken almost immediately. The first anomaly was its velocity. Measurements showed it was moving at 87.63 kilometers per second. That in itself is not unusual for an interstellar object. What stood out was the stability of its path. Instead of drifting unpredictably through the solar system under gravitational influence alone, its trajectory showed subtle signs of correction. Small deviations appeared too consistent to ignore. It was as if the object was maintaining direction rather than simply following it. That raised an early question among researchers. Was this truly passive motion or something more controlled? At the time, there was no definitive answer, but the behavior was flagged for continued observation. Then, on April 9, 2026, everything escalated. At 1422 UTC, NASA's Solar Dynamics Observatory recorded a sudden and highly concentrated burst of solar activity near the Sun's outer layer. Within that burst, a stream of helium-3 began forming an extremely rare isotope in solar emissions. But what happened next changed the interpretation entirely. Instead of dispersing into space, the helium-3 stream appeared to align into a narrow, focused channel. At the same time, instruments detected the formation of a magnetic bridge extending outward from the Sunday. NASA's Solar Dynamics Observatory recorded it first. Then ESA's solar orbiter independently confirmed the same structure. Shortly after, the ALMA array in Chile detected matching signal signatures. 3 independent systems, 3 different measurement methods, 1 identical conclusion. A directed plasma connection was forming between the Sun and 3I, Atlas. This was not a passive solar event, it was structured. And more importantly, it was sustained. Over time, the data revealed that this plasma bridge was not unstable or chaotic like typical solar eruptions. It was narrow, consistent, and stable over vast distances, maintaining a coherent structure across 140 million kilometers. That level of stability should not exist naturally. Then came the energy readings. NASA's Parker Solar Probe measured the thermal and magnetic behavior of the connection and found something even more difficult to explain. The plasma was not dispersing energy outward in all directions, as expected. Instead, it was confined within a tightly controlled magnetic tube roughly 400 kilometers wide. This structure held its shape over millions of miles, resisting natural turbulence from the solar wind. To maintain something like this, calculations suggest an energy requirement of approximately 4.2 petawatts, continuously sustained. That is far beyond anything a natural comet could generate or control. And yet, 3I, Atlas, remains stable at the receiving end of this connection. No fragmentation, no thermal collapse, no structural failure, just continuous interaction. At this point, scientists began to question whether they were observing a comet at all or something capable of actively regulating its environment. Because the behavior was no longer random, it was coordinated. And that realization forced a deeper investigation into what 3I, Atlas, is actually doing inside this system and why it appears to be selectively extracting material from the Sun itself. Because once researchers accepted that the plasma connection was real, the next question became unavoidable. What exactly is 3I, Atlas, doing with the material it is pulling from the Sun? The focus quickly shifted to the helium-3 stream detected by multiple instruments. Helium-3 is not just any solar byproduct, it is a rare isotope with extremely high energy potential, often discussed in advanced fusion research, due to its efficiency and low radiation output compared to other fusion fuels. Under normal solar conditions, helium-3 disperses naturally within the Sun's outer layers or is carried away irregularly by solar wind. It does not form stable, directed streams. But in this case, it behaves differently. Instead of dispersing, the helium-3 appears to be organized into a narrow, high-density flow. And more importantly, it is moving in a precise direction toward 3I, Atlas. This is where the interpretation begins to change. Because rather than a random solar emission, the data suggests selective extraction. NASA's Parker Solar Probe confirmed that the stream is not weakening over distance. Instead, it remains tightly confined within a magnetic structure, almost like a controlled conduit. The shape and stability of this channel suggest continuous regulation rather than a one-time burst. That alone challenges standard models of solar plasma behavior. But the most significant detail is what happens at the receiving end. As the helium-3 approaches 3I, Atlas, it does not disperse into space or scatter across the object's surface in a typical impact pattern. Instead, energy readings suggest absorption direct and efficient. The mass transfer rate recorded by deep space monitoring systems is staggering. Approximately 33 billion tons of solar-derived material appear to be involved in this interaction over a short observational window. And yet, despite this massive influx, the object shows no signs of structural disruption, no fragmentation, no overheating, no instability. Instead, it remains stable. That contradiction has become one of the central puzzles in the analysis. Because any natural object absorbing that much high-energy material from the sun would experience extreme thermal stress. It would heat up rapidly, expand, and likely disintegrate under internal pressure. But 3I, Atlas, does not behave that way. It appears to regulate the process. At this stage, some researchers began to describe the behavior in functional terms rather than purely physical ones. Instead of asking whether it is surviving the process, they began asking whether it is managing the process. That shift in language is important because it reflects a shift in interpretation. Meanwhile, new observational data added another layer. The plasma bridge itself is not static. It pulses at regular intervals, approximately every 23 seconds. These pulses correspond to bursts of increased energy transfer, visible in multiple wavelengths across different instruments. NASA's Hubble Space Telescope captured these pulses as repeating flashes along the plasma channel, almost like rhythmic energy transfer events. This introduces another complication, because periodicity implies structure, and structure implies control. At this point, scientists began comparing the plasma behavior to engineered energy transfer systems, specifically those designed for controlled fusion intake or directed energy harvesting. In those models, energy is not simply absorbed randomly. It is collected in regulated cycles, processed in stages, and distributed internally according to system demand. And that is where 3I, Atlas, begins to resemble something more than a passive object. It begins to resemble a system designed for energy acquisition. However, despite these interpretations, no direct evidence confirms artificial origin. The data remains observational, not conclusive. Still, the consistency of the pattern is becoming harder to ignore. Because every new dataset reinforces the same idea, this is not chaotic interaction, it is structured exchange. And that realization leads to the next critical question. If 3I, Atlas, is not just absorbing solar material, but regulating how it is collected, then what internal system is responsible for controlling it, and how does it remain stable under such extreme conditions? Because once scientists began treating the plasma connection as a structured energy exchange, attention inevitably shifted from the sun to the object itself and what might be happening inside 3I. Atlas, while this process continues. The first clue came from energy balance calculations. Despite the enormous inflow of helium-3 and associated solar plasma, 3I, Atlas does not show the expected thermal buildup. Normally, when an object absorbs high-energy particles at this scale, its temperature should rise rapidly, triggering expansion, fragmentation, or at least detectable surface instability. But that is not happening here. Instead, thermal readings remain oddly stable. This immediately forced researchers to consider one of two possibilities. Either energy is being dissipated in a way we do not yet understand, or it is being converted and redirected internally at extremely high efficiency. Neither option fits within standard cometary physics. Then came another unexpected detail from NASA's deep space monitoring systems. The inflow of helium-3 is not constant. It follows a repeating pattern, measurable pulses occurring every 23 seconds. Each pulse corresponds to a spike in plasma density entering the magnetic channel connecting the Sun and 3I Atlas. This periodic structure is critical because natural solar emissions rarely maintain strict timing cycles. The Sun is chaotic, influenced by magnetic turbulence, rotational shear, and unpredictable reconnection events. Yet here, the system behaves with consistency. That consistency suggests regulation somewhere along the chain. Hubble Space Telescope observations added another layer of confirmation. The plasma bridge itself appears to brighten and dim in sync with these pulses, almost like a controlled transfer mechanism adjusting flow in real time. This led researchers to a more technical interpretation. The system may not be a simple conduit, but a regulated transfer structure with feedback control. In other words, something appears to be managing the flow. At this point, the scientific language used in internal discussions began to shift. Instead of describing the phenomenon as a plasma interaction, teams began referring to it as an energy acquisition system. That change in terminology reflects how the data is being interpreted. Because the behavior is no longer random or purely environmental, it is organized, measurable, repeatable. Meanwhile, Parker's solar probe data revealed another important constraint. The magnetic channel connecting the Sun and 3I Atlas remains unusually narrow, approximately 400 kilometers wide, despite spanning a distance of 140 million kilometers. That level of structural stability under solar turbulence is extraordinary. Normally, magnetic fields in the solar corona distort, twist, and collapse under dynamic pressure. Maintaining a coherent structure across such distances would require continuous stabilization, which implies active maintenance somewhere within the system. At the receiving end, 3I Atlas continues to show no signs of damage, no fragmentation, no overheating, no loss of structural integrity. Instead, it appears to be fully adapted to the inflow. And that raises a deeper question. Is the object simply surviving this interaction, or is it designed specifically for it? Some researchers have begun comparing the data to theoretical models of advanced energy harvesting systems. In those models, external energy is not absorbed passively. It is guided, filtered, and converted through controlled internal architecture. When mapped onto 3I Atlas, the behavior aligns surprisingly well with those frameworks. Helium-3 is not scattered randomly, it is directed. Energy is not dispersed chaotically, it is contained. The system does not destabilize, it stabilizes further as input increases. Each observation strengthens the same pattern: controlled intake and regulated internal processing. However, despite these interpretations, no direct evidence confirms artificial design. The object still falls within observational uncertainty limits of known physics, at least in strict classification terms. But the margins are shrinking, because the longer the plasma connection continues, the more structured the system appears. And now, attention is shifting toward a far more unsettling possibility. If 3I Atlas is regulating incoming solar material, then it must also be converting that energy internally, and that process may explain the next anomaly detected just hours later, when the object suddenly began to change its velocity in a way that defies gravitational prediction. Because just hours after the energy intake patterns were confirmed, a new and far more concerning development appeared in the tracking data, one that shifted the investigation from energy collection to motion control. At 8:33 UTC on April 11, 2026, the ALMA Observatory in Chile recorded a sudden and highly precise change in the velocity of 3I Atlas. The object, which had been moving at 87.63 kilometers per second, abruptly reduced its speed to 30 kilometers per second. The most important detail is not just the slowdown itself, but how it happened. The deceleration occurred over a window of just 4.2 seconds. That timescale is critical. In astrophysical terms, such a rapid change in velocity for an object of this estimated mass should result in structural failure. The forces involved would normally generate internal stress strong enough to fragment or destabilize any natural body. But 3I, Atlas, remained intact. No breakup, no shock disintegration, no thermal spike consistent with frictional compression. Instead, the transition was smooth and controlled. This immediately raised serious questions within the scientific community. Because deceleration in space does not occur without a force, and that force must either come from external gravitational interaction or internal propulsion. But neither standard explanation fits the data. The gravitational field in that region of space is well mapped. There are no nearby massive bodies capable of producing such a precise and rapid slowdown, and the object shows no evidence of external impact or drag sufficient to explain the change, which leaves only one remaining category: internal control mechanisms. At the same moment as the velocity shift, instruments detected a structured electromagnetic emission at 1,420 MHz, the hydrogen line frequency. This is one of the most studied frequencies in astrophysics, often used in SETI research due to its universal significance. But this signal was different. It was not random noise or background radiation. It was structured, repeating, and directional. The emission pattern appeared to be intentionally aimed along a trajectory that intersects Earth's orbital path. This detail immediately escalated concerns within multiple agencies, because now the object is not only interacting with the Sun, it is also emitting structured signals in a direction that aligns with our planet's movement. At this stage, the interpretation of 3I, Atlas, began to split into two major scientific perspectives. One group continues to argue that all observed behavior may still fall within the range of unknown natural physics. They suggest that extreme plasma dynamics, rare electromagnetic resonance effects, or previously unobserved solar interactions could account for the anomalies. But another group is increasingly cautious, because when all datasets are combined, thermal stability, plasma harvesting, structured emission, controlled deceleration, and directional signaling, the pattern begins to resemble a system designed for purpose-driven behavior. Not random interaction, not passive drift, but coordinated function. That interpretation is reinforced by another observation recorded immediately after the slowdown event. The plasma connection to the Sun did not collapse. Instead, it stabilized further, maintaining consistent energy flow even as the object reduced its speed. This contradicts expectations. Normally, a major velocity change would disrupt external interactions. Instead, the system appears to compensate and maintain stability, which suggests internal regulation across multiple subsystems. At this point, researchers began using more technical language associated with engineered systems rather than natural objects. Terms like adaptive control response, trajectory modulation, and energy state synchronization began appearing in internal reports. However, no formal conclusion has been reached, because despite the growing pattern of structured behavior, there is still no direct proof of artificial origin. But what is becoming increasingly difficult to ignore is the consistency. Every major anomaly follows a logical sequence. Energy intake increases. Internal stability holds. Motion adjusts. Signals are emitted, and the system remains intact. This is not how natural interstellar objects behave under solar influence. And yet, it continues. As a result, global monitoring agencies have escalated coordination efforts, with NASA and ESA temporarily restricting public access to certain real-time datasets while analysis continues. And now, attention has shifted to the most important question yet. If 3I, Atlas, is capable of regulating energy intake and controlling its own motion, then what is the purpose of the signal it is sending toward Earth, and what happens when that signal reaches its intended target? Because as the investigation reached its most critical phase, the focus was no longer just on what 3I Atlas was doing near the Sun, but what it was preparing to do next. After the sudden deceleration event, scientists expected instability. Any object undergoing such an extreme change in velocity should show signs of structural stress or energy imbalance. But instead, 3I Atlas remained steady. Even more concerning, the electromagnetic signal at 1,420 MHz continued without interruption. It did not weaken. It did not drift. It remained structured, repeating, and precisely aligned. This consistency has now become one of the central points of concern, because a signal that's stable implies continuous control, and continuous control implies an active system maintaining it. At this stage, NASA and ESA both confirmed that internal coordination between observatories had increased significantly. Several datasets were moved into restricted access channels, not because the public cannot be informed, but because the complexity of the data requires controlled interpretation. In parallel, telescopes in Hawaii, Chile, and space-based platforms began focusing all available instruments on the object. The goal was no longer general observation, it was real-time tracking of every measurable change. And what they found added a new layer of urgency. The signal being transmitted by 3I Atlas is not random. It shows structured repetition with timing consistency that suggests deliberate encoding. The hydrogen line frequency is not being used passively, it appears to be serving as a carrier for organized data patterns.